Good afternoon, everyone. I'm just going to give it another minute because I can still see the attendee numbers climbing, and then we'll kick off in a minute's time. Hope you're all well and looking forward to the session this afternoon. Okay, great. So welcome everyone this afternoon to the first in this webinar series regarding on Future Flight Fridays. We've got a really exciting session for you today around batteries in aviation. So welcome, I hope you're going to enjoy the session. My name's Sheena Hindocha, by the way. I'm in the chemistry team at KTN. Also just want to say with us, we've got Nicoletta Pipiridou, who's our energy storage expert in infrastructure. Do you want to say hi, Nicoletta? And also this has been organised by our transport team. Michelle Carter, the head of transport, is here as well. So before we kick off properly, I've just got some practical stuff that I want to tell you about. So everyone is muted throughout the webinar. If you have any questions as we go through, please put them in the Q&A box. We will have time for questions at the end of the session. So as anything you want to ask, just put it in that Q&A box and we'll cover them at the end. If you have any technical issues, please put that in the chat box and someone will come back to you with details on hopefully how you might be able to fix it. In addition, the webinar will be recorded and you'll be sent a link after this as well. So to let you know what's coming up, we've got 3 brilliant speakers for you today. I'm going to give you a quick intro, and then we've got Steve from Rolls Royce, Limhi from Vertical Aerospace, and Julian from Ricardo, who are going to talk to you about batteries and aviation and their perspectives on that. As I said, we've got Q&A at the end, so any questions, please put them into the Q&A box. But what is this webinar series about? So the Future of Flight Challenge is looking at how goods and services are going to be moved around in the future. And this webinar series is looking to build on exchanging knowledge and gaining new insights. Using KTN's cross-sector reach, we're hoping we can help you build connections and find new technologies and services that will help ideas in the Future Flight programme and with the challenges. And talking about the Future Flight competition, there is a competition open at the moment. It is closing on Wednesday though, so this is really just a reminder for those of you that are looking to submit applications. You've got a few days left to finalise those and submit them before the deadline. There are 2 strands open, fast track and development, and proposals should be around creating the technology and services to enable future aircraft to fly. So if you have any questions about this competition or your proposals for it, I'm sure our transport team would love to pick them up. So please do get in contact if you have any questions regarding this competition, which closes next week. This series, as I mentioned, will be going on for a while, and it's got some really exciting webinars planned. The next one is in July on air mobility of the future, and we've got some speakers lined up for that already. There's another session on nature-inspired solutions, which sounds really great. So if you're interested in hearing about anything else or joining any of the other sessions, I suggest that you check out the website where you signed up for this session, have a look at what else is planned and register your interest. And to keep in touch with the Future Flight Challenge, there's a website, an email address, and you can follow the Future Flight hashtag on Twitter. So just to keep in touch with any news and developments as the programme continues. So this first in the series is brought to you by the Cross-Sector Battery Systems Group in collaboration with the Future Flight team. And this is a group that's convened by KTN and has additional funding now to continue as a special interest group for the next few years. And I'm going to talk to you a little bit about what that is and what we will be doing. So the cross-sector battery systems group brings together a cross-section of technology developers and end-user applications to explore opportunities and try to leverage activity across sectors to accelerate innovation. So we was originally convened by KTN back in 2018, and as I said, we've got additional funding to continue convening this group over the next few years. We're working very closely with WMG and the Faraday Battery Challenge as well to build this group and to keep it alive. And you can see some of the people that are involved there. And the key aims of this group are to open new markets for the battery industry, so introduce the community to new sectors, to new opportunities to try and grow. To promote innovation, so where are the technical gaps, where are the issues in different applications, and actually where can we accelerate some of that innovation? And identifying cross-sector opportunities to really drive that forward. In the main aim, though, is to help decarbonise different sectors, and this is what we're really striving towards, to look at different end users from rail, maritime, construction, and help them to decarbonise their processes and support the net zero agenda. So some of the battery opportunities and challenges that we've found, aerospace, and that's one of the reasons we're here today to talk to you about aviation, construction, rail and marine as well. Each of these opportunities will have its own challenges, and within each sector there are multiple different uses of batteries technologies and multiple different applications, each of which will have its own priorities, technical gaps and challenges. So it's a complex field, and that's something that has been identified by the supply chain challenges. This fragmentation across the wide range of sectors that can utilize batteries can be a challenge. You know, scale, volumes, timing, the different technical requirements all need to balance out to build that supply chain. And that's what we're trying to do within the sector group, is identify where there is synergies and where we can leverage activity to actually clarify some of the issues around this. As I said, we've worked really closely with the Faraday Battery Challenge over the past several years and with WMG. And in 2017, the Automotive Council released a set of targets for batteries for automotive applications. And you can see these on the screen here. As I said, for different applications, there will be different targets, different needs and different priorities. And WMG and the Faraday Battery Challenge have been working on this recently to identify what targets are required to drive innovation in battery production forward across different sectors. So this is where we have a question for you. So hopefully I haven't bored you too much yet. We're about to start the poll. So these are the targets for the automotive, but what are your priorities? So where do you see the technical gaps, the technical challenges from your perspective? We know that this is going to be dependent on the application. So Natasha, could we launch the poll, please? We're interested in hearing from you about what do you see as the three most important factors when considering the use of batteries in aviation? And then in the reverse, what are the three least important factors when you're considering the use of batteries in aviation? And this will just help us align to what WMG and the Faraday Battery Challenge are doing. And again, recognizing this is just a very rough and ready poll. And different applications are going to have very different perspectives. So we just let everyone submit their answers to that. I can still see some votes. Some votes are still coming in. I think we've almost reached the limit. So. And here we go. So we've got safety is really important, energy density and power density, really key areas, sort of the three big areas here. So the three most important factors there, that's great, thank you. I think have we got another question, Natasha? Yep. And so the second question is, which are the three least important? So if there was funding available, which areas actually are not there's not technical challenges that we see. There's not areas to be looked at. Be interesting to see if this maps across to the other ones. So I can see some votes coming in now. We'll just give people another couple of minutes 10 or 20 seconds just to answer the question. And then we'll move on. Really interesting results for this one, I think. I think we can end the poll now. And we can see that actually first life is seen as the least important factor, followed by recyclability and cost. So some really interesting answers there. So thank you very much for your contribution. That's great. I will feed that back in, see how it maps across to the WMG and the Faraday Battery Challenge information. This will be published, the work that is being done by WMG and the Faraday Battery Challenge will be published, we think, over the summer. So if you're interested, please keep an eye out on that. It will be coming soon. So just have one more slide before we get on to the real reason you're here. The Faraday Battery Challenge are hosting some webinars next month, focusing on 3 different areas. Building a battery business, the UK Battery Industrialisation Centre, which is a building where you can go to look at how you might manufacture batteries in different ways. And the final one, which might be of particular interest to you, is on lithium sulfur and how it could be used in different applications, including aerospace. So if you're interested in any of these, keep an eye out. They will be advertised very soon. So yeah, get in touch if you're interested in this cross-sector battery group. We're always interested in having new members and getting more people involved. So if you have any questions about it or want to hear any more, please get in touch with either myself or Nicoletta. But without too much further ado, we're going to move on to the reason everyone's here today, is to listen to our speakers. So first up, I would like to introduce Steve Mountain, who's the Global Energy Storage Lead at Rolls Royce. Steve, if you'd like to take it away, thank you.
Yeah, thank you, Sheena. That's lovely. Thank you for that. So what I've got in the pack today is just really a higher level overview as an introduction to aerospace, electrification and the energy storage. I would say the key drivers. So moving my pack on. Sheena, would it be possible for you to move my pack on, because I can't seem to click through it? Thank you. Okay, so I'm just going to break into a few sections, just give you a bit of a flavour of the market overview, where the primary opportunities are for batteries, something about the key performance requirements, a little introduction to the small propeller retrofit market as a working example, just to give you some flavour there, and then back to those key drivers that are shaping the battery pack designs. So Sheena, could you move on one, please? Thank you, and one again. So this is just how in Rolls Royce we perceive and have chosen to fragment the markets. So we see 8 major segments, all of which have some opportunity for electrification to a larger or lesser extent. And we see that I think for probably a reason that most of us understand, the early market opportunity for propulsion systems would be at the smaller end of the market, with the tending to have a shorter ranges, where batteries are highly credible and a very definite opportunity. And we've broken those into 3 subclusters of small propeller, urban air mobility, and commuter. And I'll talk briefly about each of those segments in a moment. So Sheena, could you move on one? So just before I do that, though, I think, and I apologise, I'm sure 90% of you are aware of this, but just to kind of, for those that perhaps not aware, C-rate, the battery pack as one of the underlying key metrics at a high level, and this just it's important to recognize the difference in the energy density that you will get from a pack depending on what is the C rate, which is simply the ratio between energy and power. So on this chart just illustrated, you have the cell level rate that's generally at the top end of the performance available in the market from cells, and then the blue line is, by the time you compile that into a pack, largely where you will be. Obviously there's difference depending on application, but as a general indicative measure, this is where you would be with a pack design at those different C rates. And you'll see that many of applications we'll talk about are on that steep slope between 1 to 10C, where there's a reasonable variation in the what you get. So understanding the mission profile and some of these key metrics is a good indicator as to the weight you will require on the platform, and iteratively how that drives the platform design. Okay, Sheena, can move on one, please. So just a quick overview of urban air mobility, which there's an endless variation in platform concepts that are out there at the moment, all at different stages of maturity. But the urban air mobility in itself also has different concept of operations, which drive different mission profiles. And this is just a quick, and there's no correlation, I should say, between the concept profiles and the pictures above, but just give you a flavor of the different profiles that are out there and how they result in different C rates, either a peak C rate or just as an indicative value of called RMS C rate, just to give you some, for complex wave profile shapes, mission profile shapes, just where order of magnitude where you would be with the required cell and the pack design. There's a very large spread. So one battery to be optimized for one battery module to be optimized for many is not really there, and it's if you can have a common or limited number of batteries to service many opportunities, then it's going to be picking an appropriate compromise around that landscape. Okay, Sheena, could we move on one? Similarly, for the small propeller segment, a number of different profiles and aircraft that could be retrofittable with energy storage, and I'll talk about that segment a little bit more later. But again, some level of variation across the ultimately underlying driving requirements for the battery pack. But it gives you some flavour of the pack sizes, the powers, C rates that are required in this segment. And then, Sheena, just to complete the 3 segments, one more slide, and the commuter segment. Again, this is obviously tending to go for longer ranges, so the C rates are dropping, but still substantive variation in different platforms and their requirements. So give us some flavour. Okay. And so I thought I'd just give it a little bit more colour on some of that. If you consider the small propeller market, and these profiles, I think, are largely trainer type aircraft, which is a substantial opportunity for trainer aircraft, which leave and return to the same airport, or perhaps small cross-country travels, and there's the takeoff and then some kind of profile associated with the mission. And the ratio between what the takeoff looks like and the animation does vary, even in this limited segment. So it just gives you some flavour of what you might be sizing around for the various battery packs. Next one, Gina. Thank you. This is a little more complex pod, so I'll spend a short amount of time trying to explain it. So this is our study of different aircraft types in the small propeller segment. So each of the coloured elements, if you like, is one aircraft studied, and assuming for retrofit, assuming there's no change in max takeoff weight, that we are fitting within its current design, shows which ones can be done with a battery without any changes to that max takeoff weight, and whether you can complete the original intended mission or not at the beginning of life and at the end of life. So you can see there's a large swathe of aircraft where that's couldn't be retrofitted and still achieve anything like the same mission, and in fact may not be able to take off. Whereas there is another family of aircraft that can actually complete the whole mission, and some that can complete part of the mission at beginning of life and steadily would reduce their range and mission over time. So this just gives the identify within the segment the aircraft that are retrofittable and where the opportunity lies. So it's an interesting single chart that gives some illustration of the market opportunity, at least in small propeller. Okay, Sheena, could you just move on one slide, please? So and this is just a final sign. Apologies, I've gone a bit quickly. I'm not very good at my timing, but only had 10 minutes. So just finally, so the design drivers. So Rolls Royce, for instance, we're doing full power systems, the motors, the power electronics, the battery systems, and the system controls, essentially the whole propulsion train, trying to service many different platforms, and that's a challenge with the variation, as I've shown you. But one of the things to consider is do we need to create an entirely optimized module for every single application, or is there something that is reusable and cover a subsegment of the market? And what decisions on that capacity would you have, so you can incrementally add units on, or to a larger or less extent, to deliver the capacity and still fit within the airframe and be reasonably well optimized. The C-rate design points of the modules and the capacity put into a single module is part of that decision-making process. That's a challenge across the variation. The other one that's features in quite a number of the aircraft we've highlighted is the utilization factor of the aircraft. So many want to get the utilization from the aircraft, which means a fast turnaround. So small time on ground in the course of the day, which ultimately drives high charge rates in principle. So you've either got to accommodate the high charge rate and the thermal design that would go with that, and managing that, and is it acceptable to the concept of operations, or do you look towards a swappable battery for fast turnaround and making that a fast swap system? Would you do that in an automated way? What do the interfaces look like? Of course, recognizing that charge rate is still important in some respects, in that the inventory that you need for the total operations is higher. If you're swapping the batteries, the inventory stock that you need to deliver that in the end. So there's many more batteries in this system than you would have aircraft, but you get high utility from the aircraft if that's the underlying requirement. Safety, as I think the study showed earlier on, safety is paramount in aerospace, is simply non-negotiable, and containment of all failure mechanisms required is different to the automotive industry, where you might have a 5-minute scenario where you can pull over and keep everybody safe. That's not available in aerospace, and we need to contain all of that. There are certainly some standards and tests being developed, but they're not yet comprehensive. There are failure modes that are not represented within that. So safety case, we need to cover all of that space and provide the safety argument and evidence to show that all failure modes are fully covered. And I think at this point in time, although it does happen in many safety cases in other areas, is use statistical elements as part of the safety argument, but I think the statistical evidence isn't strong enough yet to use in safety arguments, so it needs to be more absolute, that all modes are always covered in and contained in a design to a safe level. So it drives some of the pack peripheral design that will ensure that. And the last one, which is kind of important, pack design consideration, being the decision on it, but a difficult one to set a requirement against this point in time, is the cycle life, which is not strictly a performance trade because the performance is set by the mission, but in terms of the business case, the time a pack will last before it's not it needs to be replaced is a consideration, and what weight penalty you're prepared to accept for adding extra life on it is not a well evaluated study at the moment, but you can see that in application that run multiple times per day, you can run up expected life cycles in a year or less in some applications. So that's quite a high replacement model if you don't get the life, and but it is all a business case trade. Yeah, and other challenges. There's plenty of more challenges, I might imagine. Things like cell variation in a pack, ensuring you understand your position and you have the energy needed to complete the mission or any emergency modes at the end. So understanding your pack and predicting it and able to have certainty around that is key, particularly with variation is going to be a challenge. So apologies, I'm not sure where I stand on time, but that's all I have for today. I hope that was interesting.
That was brilliant. Thank you, Steve. Really interesting to see what you're getting up to at Rolls Royce. So we're going to move on now to our second speaker. We've seen some great questions come in. So again, if you have any questions, please put them in the Q&A box and we'll try and answer them at the end of the session. But our second speaker is Limmy Somerville, the Head of Energy Storage at Vertical Aerospace. So I'd like to hand over to you, please, Limmy.
Unmute myself. Hopefully everyone can hear me. Hello from sunny Bristol. It's not very often you get to say that. So we've got a bit of a whirlwind tour today. So I guess the purpose of my talk is to give you a bit of a taste of some of the things that certainly we're involved in and some of the things that are happening in the industry, and maybe take some of these discussions offline as well, which for me is the primary aim. But for those that don't know, Vertical Aerospace was started in 2016. In 2017, 6 engineers pulled together what we called our proof of concept. It was given, it was able to fly in 2018, and then we also, it flew in 2017. We then produced our first multi-rotor copter. So the first was a quadcopter, and then we ended up with a multi-rotor. I'll show you a couple of pictures in a moment. In 2019, we grew to 70 plus engineers, and then we acquired another automotive Formula One company based in Oxfordshire. And then as of now, we're 100 plus engineers, and we're working on an eVTOL concept. So I can show you, that was the proof of concept. That's the quadcopter that was mentioned previously. I'm not getting good access to here we go. Seraph, so this is the 12 rotors on this one. This is one that was flown last year. You can find some more details about that online. There we go. Slide transitions. I didn't put these in. I don't know who did this, but fantastic. And then Seraph, of course, was the first. We were the first company to release flight footage of an eVTOL capable of carrying 250 kilograms, and that was a significant step for us. But it also allowed us to prove out some of the concepts of eVTOL more generally. So loss of props, loss of power or thrust from particular locations, and then seeing how the aircraft is able to respond to that. And we're currently working on our next aircraft. So the next concept is a winged concept. And so we've looked at the rotor and the problems with the motors and electrification, and we're starting to move now towards the next stage. It's a bit of background on me. So I'm Head of Energy Storage at Vertical. And I currently chair a Eurokai working group, which is looking at certification writing standards, both closely aligned with EASA, but certainly to meet the EASA SC VTOL requirements. And so I lead that group in terms of writing those standards for energy storage and battery systems. So this is the bit where we go fast. The first thing I guess just to put out there is that eVTOL or electric flight generally gives us a change in the fundamental assumptions that we made with batteries, and certainly batteries with respect to automotive. I'll give you a couple of examples. So one of those is this high power demand. I'm so glad I didn't go down the same routes that Steve went down. I very nearly did. I didn't get to see his slides before I did this, but I'm glad that we've aligned nicely. But essentially we've got this high power demand. Hopefully you can see my cursor. If not, it's there now, but right at the beginning of this flight here. And that power demand is really, really significant. So that power demand, certainly for an eVTOL, that initial vertical takeoff, we're talking maybe as much as 100 to 200 times what an automotive application would see. But then when we drop to this traditional flight, so this long period of altitude where we're just flying in forward flight, and certainly this would be with a winged concept, that power demand drops to something that's more typical of a plug-in hybrid electric vehicle application. So you're dropping to 1, maybe 2C. And so you've got these definitions where the same battery has to provide this exceptional power demand at beginning of flight, and then at end of flight, and then at end of flight, that same power demand is required in order to be able to land. Now this is for eVTOL. CTOL airplanes would give us different opportunities here. So we could use that initial demand. But actually that pushes lots and lots of requirements back to the battery system, and it changes lots of the systems. And aerospace generally gives us an opportunity to look at things differently. And here's just a couple of examples to show you that we're currently working on. One of them is state of charge. So in automotive, for the most part, you're using a large, Tesla Model 3 uses 97% of its state of charge window. In aerospace, that just isn't possible. So we add this minimum power requirement that sits right at the bottom, and that's because of this high power demand. We just lose the available energy because we have to meet a power demand without hitting the lower voltage limits. We also then have to add in this reserve requirement, which was mentioned. So this is the, we come into land, we're not able to land, we need to then recirculate wherever it is we're going to land and land again. Then we're going to lose some for balancing. And then in this particular example for state of charge, we have a significant impact of the state of charge on the available. So in a normal car, you just stop. In aerospace, the SC-VTOL at least, it pushes requirements onto you that says, if you don't meet this demand, you have to assume your very worst case. So at the moment, the standards that are being written say, if you think that you're if you've run all your testing and you were 30% out once, what that essentially means is you have to assume you're always 30% out, right? And so you go through that flight profile and you essentially have to allow that additional 30%. So now you can't fly as far because you've had to set in this 30% limit. So suddenly, very small gains in state of charge, maybe a 1% gain in state of charge, because it's such a large portion of the available energy, maybe 30 to maybe 60 to 50% of the total available energy, actually things in automotive that didn't make any sense, things like single particle modeling on the vehicle or indeed off the vehicle during charge events, that becomes very, very lucrative in terms of providing total energy, because it gives you, 1% total state of charge would give you 3% additional range. This has largely been covered by Stephen. I don't want to go through it again, but it's essentially trying to pull together exactly where this value comes from. I've used Toyota, BMW. I've used the 95% nickel, 30% silicon, which is the sort of. But what happened historically during this large growth period between 2012 up to largely last year, maybe 2018, was that we knew where that technology improvements were going to come from. What we're starting to see are cell suppliers that previously thought that maybe 95% nickel was going to be possible. Actually, they brought out cells that then were removed again because actually it reduced life too significantly. And so the question then becomes, where does that come from? Solid state gives some opportunities, but certainly, in terms of what I can see at the moment, we've maybe got some pseudo solid states and gel technologies and some other applications, but largely it's coming from cell pack engineering. And I've set a target that really becomes feasible in terms of meeting the long range targets, both for ourselves and for the market more generally. Another thing is cell supply. So this is the total eVTOL market as projected according to the Porsche eVTOL report compared to other individual companies within the automotive space. So when you want to go and, if I want to go and talk to a cell supplier, you can imagine I'm not carrying anywhere near the sort of weight that maybe I need to as a single supplier. And it really feeds into what I think is, we're going to come back to it, but we're going to come back to this discussion around a more unified approach is needed for aerospace because we don't have the volumes that automotive have had historically. Just a brief touch on certification. So battery systems more generally we've obviously got application and transport, which everyone will know about. We've then got this SC-VTOL, which is specific to VTOL, but lots of the applications are starting to apply into more electrification of aerospace more generally. We've got the typical standards, which are indicated here in gray, and then this DO311, that's a rechargeable lithium-ion standard. The problem is, the largest category of batteries is anything over 100 watt hours in this case. Steve just showed some cases of batteries that are up at 600 kilowatt hours maybe, I can't remember exactly, but it's a significant change in terms of the battery. And so the minute you have to apply DO311 requirements, it forces you to put in an awful lot of additional safety and unnecessary safety in lots of cases. And so we've been leading the side on, but has had an awful lot of support from various members. In fact, the industry is rewriting some of these DO311 standards specific to very large applications. So systems that are 100, 200 kilowatt hours, and how we ensure that they're safe, whilst also ensuring that the industry isn't killed by unnecessarily problematic standards from previous. So I'll talk just very briefly. I count a minute and a half. So we're not going to have time to go through all of this, but I just want to show you this is a light system. So this is a bit like stopping at the green's good, red's generally bad, and orange is somewhere in the middle. And I've tried to pull out the 7 different aspects of the aerospace battery capability today, and certainly in respect to the UK. And I've sort of pared that down to 7 key areas, and I'll just speak on those very briefly on each. So pack design, we need an aerospace design. Automotive doesn't cut it. repurposed automotive doesn't cut it. And those that are looking maybe at aerospace design, at the moment they're too niche, they're not getting enough involved in terms of certification and the requirements around that, which will drive the design. So concepts are okay, but really ending up with a certified option is more difficult. Batch management system, of course, is a critical aspect. In our opinion, we're really aiming for a common new aerospace. The custom new aerospace, which is what lots of people are doing, is going to ultimately, I think, drive a lot of cost. And I don't think it's necessary. So I personally don't think, maybe in the software, but certainly not in the hardware, there isn't enough differentiation that should drive any company, in my opinion, to try and to do that solo. I think it's where the software is coming in a lot smarter. And so working together and collaboratively on that would be good. Battery components, I think, is probably largely a non-issue in terms of getting there. Cell supply, I touched on briefly. There's lots of problems with cell supply and more generally how we get it. I've got personal concerns in terms of the niche market and how these smaller suppliers, how they can meet the technical capability that currently sits with primarily Asian, but other tier 1 suppliers that are currently going into automotive. Manufacturing remains many of the same issues. Certification testing. So I cover certification and testing for design. The facilities just don't exist in the UK. So it's fine saying that we have an automotive facility that can do cell testing, but not only do we operate at 800 volts, but because of our peak power requirements, in some cases you're talking about megawatts of power, and lots of the facilities we're talking about are well below that. And even if they are able to meet it, the minute you start getting to certification, there's a number of tests that require repeated cycles on a facility that's 2 or 3 megawatts. Well, that means you're using up someone's entire capability because they've had to parallel all of their channels up to get your battery on. And you're talking about utilizing that day after day. It becomes very, very cost prohibitive at that point. And so we need to look at specific facilities for automotive, and that needs to be collaborative. No one company, not even Rolls Royce, could bear the cost of something like that. And that whirlwind tour is largely over. So thank you very much. There's the 3 key summaries, but yeah, thank you. Thank you for your time.
That was brilliant. Excellent, Limmy. Thank you very much. Really interesting take on it. It was great to hear. So we're running a tiny little bit behind, but we've still got plenty of time for questions. So I'd like to introduce our third and final speaker of this session, Julian Dunn, who's the head of energy storage at Ricardo. So Julian, if you'd like to take it away. Thank you.
Awesome. Thank you for the introduction. So yeah, going to cover probably some of the similar topics there to Steve and Limmy, but from a slightly different perspective. So for those that don't know, let me just see if I can move the slides on. Don't seem to be able to move the slides on. So okay, could you move the slide on for me, please? Thank you. So for those that don't know Ricardo, we're a global consultancy providing expertise in energy and environment, clean and efficient propulsion systems for mobility, integration of these systems into products across a number of different sectors, from two-wheeler, urban mobility, through passenger car, truck, bus, rail, marine, aerospace, and power generation, to name a few. Obviously, the discussion today is on aerospace. We look at the test and validation of those systems and niche manufacture as well as we do a lot of work in assurance and certification, predominantly in the rail industry at the moment, but looking cross-sector as well at that. And we also have a strategic consultancy arm and training around all of these areas. So that's a very quick introduction to Ricardo. So today I think we'll touch on three main areas. So there we can see the virtual product development, so rapid concept, digital twinning. We'll look at the thermal management and BMS strategy, which are some key areas of development that were introduced by Steve and Limmy. And then we'll look a little bit at test and validation piece as well. So on the left-hand side there, you can see sort of the spread of services that Ricardo offer in the aerospace domain. So in the blue areas are engineering consultancy, so around design and release for manufacturers, the systems engineering and the management of complex systems and requirements, thermal systems, virtual product development, which we'll go into a little bit, and then the rest in grey there around where we have engineering service and test and low volume manufacture capability as well. Okay, so if you could move to the the next slide. Thank you very much. So this is, most people recognize this traditional V cycle for product development. It's very good and robust and has been used many times, but what we're seeing more now is we need more agility into the system. We need to be faster. We need to get to market quicker, reduce the time, because the attribute set for electrified products is evolving very quickly. So you need to be able to evolve products of high quality in the shortest time possible. So the kind of backbone of this is the right first time based on a digital twin. I'm using some accurate model-based control as well within that to using your digital twin, and then you can have a very good model-based control. Some of the tools that we use in the battery space are multi-domain modeling, so coupling the thermal, electrical and aging model. I saw in the survey that second life and recycling not such high priority at the moment. The big focus was around energy, power, energy and safety. So having models that can predict how not only your battery will perform as you've designed it and installed it, but how that will evolve over the life of the different duty cycles that we've seen presented earlier on is absolutely key. And then we've seen how highly demanding some of those duty cycles are. And so the cell life potentially will be quite short in some of those very aggressive duty cycles. So finding a second life model to share the investment and the cost of the battery systems could be an interesting business opportunity there. So having the models that maybe pull batteries out of service before they've met their end of life, so they have a useful second life, rather than using them until they are unusable anymore and then they don't have a second life, may balance. So looking at lots of those within modeling domain. Okay, if we could just move on to the next slide, please. Thank you. So we've all got our own little diagrams. So at the top right there, we've captured the sort of requirements around the takeoff and landing for different applications there. Just to recap, obviously it's very high power demand in the takeoff and landing phase, the climbing, descending, sort of medium, and then the cruise, the lower power, and we have to have the same system that delivers all of those. So underneath there, we've got some of the typical thermal solutions that you may look at, ranging in C rates. On the left-hand side, you've got air-forced, air-cooled system, which typically in legacy we see around 1.5 C limit for those systems, which probably wouldn't carry across to all of the duty cycle that we've seen above. Then as you increase in thermal performance, you go through cold plate refrigerant, which takes you up to about 2 C, cold plate liquid cooled about 3 C, and then into immersion or direct cooling, which can take you to 6 C and beyond. So those are all technologies that Ricardo have been applying into our, I guess, our traditional sector, so passenger car, truck and bus, commercial off-highway. We're starting to look at those now into different applications, and it's really around the design for high performance battery pack. Okay, so if you could move to the next slide, please. So this gives a little bit of a summary at the higher end power applications for those batteries. So if you see at the top left, maybe my cursor will work, maybe not, the immersion cooled module on the Ricardo test rig, the white box there. So that has 21700 cylindrical cells. We have a cold plate and an immersion, a Ricardo IP immersion module, so it's our own IP. We've tested those back to back to have the impact on fast charging scenarios, high power scenarios, what the temperature differences between cells, what the temperature rises within the cells during some of those scenarios, and benchmark that performance. So we've done that both for cold plate and immersion. We've also got agreements with about 14 immersion fluid suppliers where we look at the different material properties that they have, and we're doing some testing with different fluids as well. So we've got a good understanding of both the real application of this technology and the different fluid suppliers and the benefits and trade-offs that some of those provide. It's worth saying, obviously, that weight is an absolutely key attribute for aerospace. So Ours is a partial immersion cool concept, so it's not fully immersion, so that reduces the weight, the amount of fluid within the system. And we've seen, as you can see there, sort of 45% improved power density versus the cold plate with the same cells back to back. On the right-hand side, you can see the pouch cell variation of that. So that's another immersion cooled module that we've done the design, simulation, analysis, and do test on. Underneath there, you can see some high power applications. So immersion cooling is actually coming to market through the McLaren have taken the speed tail to production with an immersion cooled technology battery pack. That's in the press. You can probably see the link at the bottom there to read about some of the technical specifications. So yeah, it's an emerging technology. It's starting to come to production in passenger car and the sort of niche high performance area. What we want to do as well is not just extract power from the battery, but improve the life and the safety of the battery pack. So we're looking at how the immersion technology performs from a safety perspective, how it can mitigate some of the thermal runaway and fire propagation. So there are different standards in passenger car, emerging standards in aerospace. So for example, in passenger car, you have single cell provoked into thermal runaway. And then in aerospace, it's emerging, but it looks like they're going to move towards maybe 3 cells provoked into thermal runaway at the same time. And looking at how your design can mitigate that to provide a safe solution, because as Steve mentioned, I think safety is a non-negotiable anywhere, but particularly in aerospace, your time frame for mitigation is very different from passenger car. You can't just pull over and stop. At the bottom there, we have high accuracy BMS. So Ricardo's got its own BMS hardware and software. We've developed algorithms on very high powered applications. And I think, as Limi touched on, accuracy of SoC during those very high power applications is absolutely key. You don't want to lose track of where you are for your SoC. With the regulations and standards in aerospace, you get penalized if you do lose accuracy, and then you have to carry that overhead through into production. So having that accuracy is really, really important. If we can move to the next slide, please. Okay, here's just a few examples of some of the projects we're currently doing around this immersion cooled technology. So at the top left-hand side, we're looking at the immersion cooled versus bottom cooled. So we've got some test results on that if anybody's interested, so we can show you the performance and the safety testing on that technology. That's a collaboratively funded project. On the top right hand side there, we're looking at the characterization of dielectric fluids in a cool pack. We're doing both the simulation and testing on that. The bottom two are then full application, so a supercar OEM BEV battery pack. So that's looking at extremely high performance for track level of performance, but also a road going vehicle. So you have to balance the energy power conundrum that we talked a little bit about. And then on the bottom right is applying some of this immersion cooled technology to an eVTOL aerospace application in a upcoming collaborative program. Hopefully shortly we'll be able to talk a little bit more about that in detail. Okay, if we could move to the next slide, please. Okay, so this is a little bit around our thermal runaway testing and modeling. So it's clearly a key consideration for safety, how the cell performs when it gets too hot, how that propagates through the pack, and how do you mitigate that in design. So on the right hand side there, you can see a lot of our thermal runaway and venting modeling. So there's the top one's on a cylindrical cell, the bottom one's on a pouch, and how you can mitigate that. The key bit here is to understand how that validates against real world test data. So we're doing a lot of testing and benchmarking around thermal runaway at both module pack and pack level as well to get good validation for these models. Okay, if we could step through to the next slide. This a little bit here on testing. So yeah, Limi highlighted some of the challenges on some of the larger eVTOL or aerospace applications where you've got very, very high power levels on big packs. We've been testing high performance packs for a number of years now, both functional testing and abuse or safety critical testing. So you can see some examples there of some drop, intrusion, fire testing and characterization testing. So through all of this, we've not only learned obviously how to perform the test, but the subtlety in how you execute and provoke the test. So thermal runaway is a good example. There's a number of ways to put a cell into thermal runaway. The way in which you do that can affect the test results and therefore correlation to any modeling activity you've got. So understanding not just the real world performance and the digital domain, but understanding the subtleties of how you have variation in that depending on how you provoke and execute your testing. We've done a lot of test plan optimization, so how you can reduce the test time without increasing risks. We had a little bit of discussion on statistical testing and using that, and perhaps not mature enough in aerospace yet, but using other techniques where you can use complementary digital validation versus physical validation, and also optimization of the physical validation to reduce the time and number of samples through testing. Okay, I'll just wrap up as we're coming through to the 10 minutes. Thank you very much. So in terms of what Ricardo are doing in battery development, these are some general topics here. So we're reducing the product development and cost. That's absolutely key, getting your products to market without any impact on safety and quality. They must be safe and of high quality. They've got to have a competitive attribute set, and they've got to be right for the application, and that's moving very quickly. The product warranty and risk and the designing for future complexity is key as well, to make sure when you put something into market that you have a robust, reliable product that you don't have any ongoing issues with. Managing the complexity for future legislation, requirements, customer needs. And the last one then, I think we probably came up as lower importance, I think, to the attendees, but something we really need to keep our eye on as well is optimizing for circular economy. And it's really important if we're going to, maybe the volumes were low. I think Limi showed that plot of the volume of batteries compared to maybe the passenger car market is low. But if the technology is to be promoted as a clean and sustainable option, then it is important that we address all stages of the development and make sure that the products we're developing not only serve in the first life, but they have an end of life, a recycling scenario that provides that full life cycle benefit and is comparable to existing technologies at the moment. So that was a very quick run through. If we've got any questions or anything that we want to go into further, I guess we can drop into that now into the Q&A session.
Excellent, thanks Julian, appreciate it, really interesting talk. So just thank you to all the speakers today. It was really interesting to hear the different perspectives. So we've had quite a few questions come in. I think some have been answered in the chat, but we haven't got a huge amount of time left, so I think there's a couple that we can definitely cover. One is on the safety aspect. There was a few questions on safety, and one that's come in is some of the mentioned safety and some specifications for testing. Can you elaborate on these? That was to Steve.
Yeah, I think let me cover this one. The current one that is the reference point is the DO301 standard. So that's the current reference, but as Lemmy says, it's got some headwind challenge in it. It made overdrive the pack design and yet miss some other features. So there's a lot of other work, but that's the a point of reference for the moment. I think it sets the tone for where the industry is at, but there'll be movement on that, I think.
Brilliant, thank you. Does anyone want to add any other comments? Lemmy, did you want to add anything to that? Or?
No, I think that's yeah.
Brilliant. One of the other, there's several comments in the Q&A box around hydrogen. I just would like to note to the audience that we actually at KCN also have a hydrogen economy special interest group that is running alongside this cross-sector battery group. They are connected, the teams are very close and working together, so there is that connectivity as well. But one of the questions that came in was, are any of the speakers considering alternative energy sources, e.g. hydrogen, or do they believe the future battery technology will meet the current their requirements? So maybe we could start with Limmy on that one.
The short answer is I'm not a hydrogen specialist. I've done enough reading around it to know that there are some significant challenges, and I would be interested to see any market, maybe automotive to begin with, deal with. The problem is the weight, and I don't think the weight question has been answered sufficiently for my opinion yet, certainly not for eVTOLs.
Excellent, thank you. Julian, do you have anything to add?
No, nothing, sorry, on that one.
And Steve, any thoughts on the hydrogen, use of hydrogen?
Yes, I think so. We are looking at it. We have got some activity. It is an area of interest. I think could have its place in some segments. So yes, it is it's not. It won't replace. It's not a direct competitor for batteries. There's just a potential space for it in the overall aerospace landscape. So it's. But it won't replace batteries completely, like it would never do in cars either. The reason the metrics work in some circumstances, but definitely not for all.
Sorry, Sheena, just like to add to that in terms of looking at hydrogen both in fuel cell and as an alternative fuel. We are doing some work around the full LCA impact of that and where that may bring to where batteries may not be the right solution from that perspective, where you have a high energy demand. So yeah, we have a lot of that under consideration at the moment.
Brilliant, thank you. And just to add, if you're interested in the hydrogen special interest group, you can contact Nicoletta or myself, and we can keep you informed about that activity as well. So there was just a couple, we only got a few minutes left, so a couple of other questions. One says, how long do you think it will be before battery technology can be applied to the military fast jet sector? And what do you think this will look like? I don't know if anyone would like to take that as an opinion.
Well, I don't think we can really talk about that sector easily. There is activity. You got to remember that energy storage can be used in short dynamic support of engines, for example. There are, much like it starts in a number of sectors. It doesn't drive the whole thing, but there's some use cases where it could work. So it's yeah, but those are not for broad discussion, if you like.
Brilliant, thank you. Julian?
Perhaps just a comment. I think in terms of primary energy source, batteries, but are a solution, but they obviously provide a solution where or applications where it doesn't have to be the primary energy source, so you can have alternative systems, and it depends what you're trying to achieve. Is it a performance benefit? Is it a fuel consumption emissions reduction? But I think there may be some secondary systems it may look at first rather than primary. But yeah, it's probably a bit more of a detailed discussion, that one.
Excellent. Limi, did you want to add anything, or?
No, definitely not.
Brilliant. So we didn't get through all the questions, and there's a couple more to go, but we'll try and get those answered offline with the speakers and send the responses around. Just before we sign off, I just want to thank all of our speakers again today, Steve, Julian, Limi. Excellent talks, it was really interesting. Thank you for coming to share your knowledge with us today. And just a reminder, if we can move the slide on, please, Natasha. A reminder that this is the first one in the webinar series, so if you're interested in signing up for any of the others, please go check out the website where you'll find them all, but the next one is on the 24th of July and has a focus on air mobility of the future. And next slide, please, Natasha, thank you. And also the Faraday Battery Challenge webinar series is also running throughout July. And if you're interested in that, that will be advertised very shortly. And there should be some really interesting talks there as well. So I'd just like to round off by saying, please keep in touch with us if you're interested in the cross-sector battery systems group or the hydrogen special interest group. Please do get in touch with myself and Nicoletta, and the transport team, as always, is always there to help as well. So please come and talk to us. We love hearing from you, and thank you very much for attending today. It's been a really great session. I hope you enjoyed it, and have a wonderful afternoon. I'm not sure the sun's out where you are, but if it is, enjoy it. And thank you very much. Take care.
Thank you.
Thank you.